Hey there, it's Shannon Metric-Myers, and today we're going to get the big picture idea of initial value problems. Still, we're not actually solving a differential equation, but you get a preview of what's to come. So today we'll be finding a solution of a first and second order initial value problem given a one or two parameter family of solutions. Determine a region of the xy plane for which a given differential equation would have a unique solution. And then lastly, use a theorem which guarantees the existence of a unique solution to see if it's applicable given some differential equation in an ordered pair. So here we go. Let's warm it on up by determining if the given point is on the graph of the function. So one of those so easy it's hard kind of things. We've been given an x and a y coordinate, so let's just plug them in. So y is 18 minus 3 equals x, which is 2 cubed, plus 5 times x minus 3. So all I did is put, oops, sorry, not x, my bad. X is 2. And all I did here is in for x, I put 2, and for y, I substituted, I replaced y with 18. This is from our ordered pair. Cool, cool? All right, so we want to know, is this equal? If so, then the point 218 is indeed on a point on the graph of this cubic equation, this polynomial. So 18 minus 3 is 15. 15 equal to, is that equal to 8 plus 10 minus 3? Well, it looks like it. 15 is indeed equal to 15. Check. So the answer is yes. Groovy? All right. We are often interested in problems where we want a solution, y at x, of a differential equation. Remember, DE is differential equation, so that y at x also satisfies conditions that are imposed on the unknown function, which is called y at x, and its derivatives. Add a number x0 on some interval I containing this x0, the problem of solving an nth order differential equation subject to n side conditions specified at x0 would be, we want to solve the nth derivative of y with respect to x in this case, equal to just a general format, lowercase f at x, y prime, all the way down to the n minus first derivative. And now it's subject to conditions. So y at x0 would equal to y0. If you had a second order differential equation, you'd have y prime at some x0 equal to y1. This is supposed to be a 0 here. And etc. until the n minus first derivative at x0 would equal to y sub n minus 1, where y0, y1, all the way down to y sub n minus 1 are arbitrary constants, is called an nth order initial value problem. And we shorten that often by saying IVP. The values of y at x and its first n minus 1 derivatives at x0. So this business, y at x0 equal to y0 y prime at x0 equal to y1 all the way to the n minus first derivative at x0 equal to y sub n minus 1 are called initial conditions, which, how do you think that one is abbreviated? You got it, I see. Solving an nth order initial condition problem often requires finding an nth parameter family of solutions, one happy family of solutions of the differential equation, and then using the initial conditions at x0 to determine the n constants in this family. The resulting particular solution is defined on some interval I containing the number x0. So let's look at this geometrically. Consider cases n is 1, which would be a first order differential equation, and n is 2, which is a second order DE. So to make it an initial value problem, we'll have an initial condition or two. So first order would be, you'd have this dy dx equal to some function of x and y, and it's going to be subject to y at x0 is equal to y0. And if you have the second order differential equation, you would have a function of x, y, and y prime, and that would be subject to two conditions. You would have y at x0 is equal to y0, so that's a point on the graph of the solutions. That gives you your specific particular solution. But then you also get the slope. So you get y prime at x0 is equal to y1. So y1 is the slope of the graph at the point x0, y0. So for the first order IVP, we are seeking a solution, y at x, of the differential equation y prime equals f of x and y on an interval I containing x0, so that its graph passes through the specified point x0, y0. For the second order initial value problem, we want to find a solution y at x of the differential equation y double prime equals f at x, y, and y prime on an interval I containing x0, so that its graph passes through the point x0, y0, and the slope of the curve at this point is the number y1. Cool, cool? All right. Initial conditions derived from physical systems, where the independent variable is time, which is denoted by t, and where y at t0 equal to y0 and y prime at t0 equal to y1 represent the position and velocity respectively of an object at some initial time t. All right, so now let's just take a look at some big picture ideas. So let's say the first graph is a graph for the solution curve of a first order order initial value problem. And this one will be the solution curve of a second order initial value problem. And we'll do it in terms of x and y. And let's just say, I don't know, it goes through some interval. Doesn't really matter, it's just generic. So this here on each of them would be the interval I, which of course contains x0. All right, so now let's zoom it in. So you can have all kinds of different looking solutions for some solution curve depending on your value of C. They can look quite different. So I'm just going to draw in just some random solutions. So let's say that we've got one that looks like this, and then you put another constant in there because you've got a parameter C, and let's say that it's looking more like that, and so on and so forth. You might have this guy just looking like this, and let's say that the point x0, y0, let's say that is right here. Okay, so that's our x0, y0. And so the initial condition has our graph. Let's just say it looks kind of like this, and it goes through that point. Groovy? Okay, so now suppose we've got some second order initial value problem on this side. So again, you know, you could have just different looking curves depending on what your constants are, and suppose this right here again is our x0, y0. It doesn't have to be the same, you know, thing. I'm just doing it randomly. So basically what we have here, suppose this is the shape of the solution curve when that passes through x0, y0. You're also going to have this situation, right, where we've got the slope, and the slope is y1. So it gives you even more information. Groovy? All right. So now, next we have first order initial value problems with a one parameter family of solutions. Assume that y equal to 1 over quantity 1 plus c1 times e to the negative x is a family of solutions for some first order differential equation, y prime equals y minus y squared. Pretty soon you'll be solving stuff like this, but let's check this out graphically. So I went ahead and took the liberty of, you know, putting in different constants for c1. I haven't really done a fraction yet, so let's do a fraction as well. Y divided by quantity 1 plus 0.5 times e to the negative x. And then I'll also go and do the negative. And so y6 will be 1 divided by quantity 1 minus 0.5 times e to the negative x. Groovy? So there's going to be 6 different graphs. Let me make sure we get different colors. I think they're all slightly different colors. Groovy. And then I'm going to go to graph, and check it out. We've got all this different information. Um, and so this is, you've got your different graphs. This one was when you have 1/2 in for C1. This is when we have +1 in for C1. This is when we have +5. And then the negative values, of course, end up flipping over that y-axis. So we end up having a -5 for C1. I just wrote it as minus instead of plus a negative. This would be a -1, and this is the -1/2. Cool, cool? All right, so I'll go ahead and copy this. This will be for C1 equals 0.5. This one is for C1 equal to 1. This white graph was for C1 equal to +5. And then the yellow, C1 equal to -5. The orange was for C1 equal to -1. And that purple was for C1 equal to -0.5. And that original equation, of course, was all for y equal to (1/1 plus C1 e to the -x). So you've got all, infinitely many solutions, and depending on what that constant is. I need to take a look at finding C1 when x is -1 and y is 2. So n for y, I'm going to write 2. 2 is equal to 1/1 plus C1 e to the -2. So n for the y, I put 2 because of that initial value condition. And then n for the x, I put, whoops, it should be, sorry, my bad, -1. So I'm putting that one in here, and then y is 2 in there. Groovy? Okay, so now let's check it out. So 2 times 1 plus C1e, so e to the -1 is just e, would be equal to 1. That would give us 2 plus 2C1e is equal to 1. And then 2C1 times e is equal to -1. C1 times e is -1/2. So C1 is equal to -1/2e. And I divide both sides by e. So, coming back to our graph, fingers crossed, let's put in 1/2e into our graph. Second insert times. Second e, I'm just going to retype it to the -x, and this would delete. And that should be good. And we're going to graph it. Let's do a different color. Pink. here, when x is -1, do you see right here, if we go to calculate value, if I put in that x is -1, enter, y is 2. So we did it. So let's go ahead and copy this. We ended up getting y equals, actually, put it over here. Y equals 1, we didn't clean it up at all, over 1 plus -1 over 2e times e to the negative x which provided us our particular solution. Groovy? All right, so here we go. Second order initial value problems with a 2-parameter family of solutions. So let's just look at an example here. We've got x is equal to c1 times cosine t plus c2 times sine t. It's a 2-parameter family of solutions of the second order differential equation x double prime plus x is 0. Please find a solution of the second order initial value problem consisting of this differential equation and the initial conditions that x at pi over 2 is 0 and x prime at pi over 2 is 1. So we start with x is equal to c1 times cosine t plus c2 times sine at t. Now when I differentiate x with respect to t, or in other words get x prime, I'm going to get negative c1 times sine at t and then plus c2 cosine at t. Remember that the c with the subscripts, those are constants because we're differentiating with respect to t. Groovy? All right. So looking at x evaluated at pi over 2, we just plug in pi over 2 wherever there was a t. So you'll have c1 times cosine at pi over 2 plus c2 times sine at pi over 2. Well, cosine at pi over 2 is 0, so that first term zeroes out. The second term is going to give us c2 times 1, which is just going to be c2. Groovy? So we have basically found that x at pi over 2 is equal to c2, but what was x at pi over 2? Perfect. 0. So 0 is equal to c2. And that was because x at pi over 2 was equal to 0. All right, so now here we go. X prime at pi over 2, looking at that second equation dx dt, will be negative c1 times sine at pi over 2 plus c2 times cosine at pi over 2. So all we were doing is in for our t's, we plugged in on both of these equations, we plugged in pi over 2. Now we also know what c2 is, right? c2 was this 0 here. So now x prime at pi over 2, just simplifying here, is going to be negative c1, sine at pi over 2 is 1, plus, well, c2 is 0, and cosine at pi over 2 is 0. So x prime at pi over 2 is just negative c1. But what was x prime at pi over 2? Perfect. X prime at pi over 2 was 1 is equal to negative c1, so c1 is negative 1. Add in pink. So, plugging all this stuff back in, we will have our particular solution. So at the end of the day, we will get x is equal to c1, which is negative 1, cosine t, plus c2, which is 0, times sine at t. And so x is negative cosine at t is that solution. Cool, cool? All right. Now, let's take a look at example 2. Determine a region in the xy plane for which the differential equation x times dy dx equal to y would have a unique solution whose graph passes through a point x0, y0 in the region. So this one's, I don't know, it's like kind of a so easy it's hard problem because we haven't been given this, this theorem yet to give us a stronger basis. But let's take a look at it. Dy dx, which is the slope, remember, of the graph of the solution. They're giving us the slope, not the function, or the slope function. So if I isolate, we'll get y over x. And recall that y over x, the part of it, is equal to f of x and y. So if I take a look at, the domain of f of x and y, and this comes from way up here, remember? This guy right here. So here, the domain for x is going to be what? X can't be equal to 0, right? So you'd have minus infinity. I'll put this in as an inequality. So we'll have x is a real number, right? Which is less than 0, or x is greater than 0. Y can take on any real value, right? So y actually, I'm going to just put them together. So this is for x, and then y, because it's for the function in x and y. So y, therefore, can be anything. So negative infinity is less than y is less than infinity. But we do have this issue. They have to be overlapping, right? So x has to be anything other than 0. So here we go. If we just take a look at the relationship between y over x and that as a slope, are you all cool with the fact that if you look at the different quadrants, right? So the slope here, so dy dx in the first quadrant would be positive, greater than 0, right? And also in the third quadrant, it would be greater than 0 because both y and x would be negative. And then in the second and fourth quadrants, they would be less than 0. So the limitation, for what x can take on, and the fact that you're going to wrap this into two different intervals where you can get unique answers in either one of these planes. So it would be the plane x greater than 0 or the plane x less than 0. Cool? All right. When considering an initial value problem, ask yourself questions about existence and uniqueness. Because we always like when something is unique, right? So for existence, does the differential equation dy dx equal to f at x and y have solutions? Do they exist, right? Do any of the solutions pass through the point x0, y0? Uniqueness, when can we be certain that there is precisely one solution curve passing through the point x0, y0? When do we know that? So we've got this handy dandy theorem about existence and uniqueness. So the existence of a unique solution, and these are for first order initial value problems. So here we go. Let R be a rectangular region in the xy plane defined by A is less than or equal to x, which is less than or equal to b, and C has to be less than or equal to y, less than or equal to d. And remember, because you're in a function of x and y. And that contains the point x0, y0 in its interior. If f at x and y and the first partial of x with respect, or of f rather, with respect to y are continuous on the closed interval from a to b, then there exists some interval I0, which is x0 minus h, comma, x0 plus h, where h is greater than 0, contained in the interval from a to b, and a unique function y at x defined on this interval I0 that is a solution of the initial value problem. So remember that problem was solving dy dx equal to f at x and y, subject to y at x0 equaling to y0. So for example 3, we want to determine whether this theorem 1.2.1 guarantees that the differential equation y prime equal to the square root of y squared minus 9 possesses a unique solution through the point 5,3. So if we take a look over here, remember this part is f of x and y because y prime is isolated. So think about continuity of f of x and y. X can take on any value, right? So if we look at the domain of f, make sure I wrote the right domain of f, which is f of x and y. Do that. All right, so x has no limit, right? So x can go minus infinity, less than x, less than infinity, right? Now, for the function of x and y doesn't have a limit either, right? Minus infinity, less than y, less than infinity. So it checks off that particular value, right? Or that particular condition, we're cool. But what about the first partial of this function f with respect to y? So if we take a look at the first partial of f with respect to y, that's going to equal to what? We're looking at the square root of y squared minus 9, right? So, beautiful. We would end up getting 2y over one half, sorry, whoops. So we would get, that's going to be the first partial with respect to y of y squared minus 9, that quantity to the 1/2 power, right? Which is equal to, beautiful, 1/2 times y squared minus 9 to the negative 1/2 times 2y, using the chain rule. The 2's will divide out, and then we're just going to get y over the square root of y squared minus 9, which of course has a discontinuity, right? Y can't be equal to 0. So it's continuous on minus infinity less than y less than 0, and 0 less than y less than infinity, right? Other words, y can't equal 0. So let's just take a look here. What is our x0, y0, right? Because we need to figure out f of x and y. So f of x and y, we're supposed to plug in 5 and 3, right? So there's no x value to plug in. So when I plug the 3 in for 9, I would get 3 squared minus 9, which of course is 0. So I'm just plugging in the 3 for y. There was no x to plug in, so I didn't need to worry about x. But do you see how this doesn't work for this requirement, right? So the answer to this would say no, would be no. The theorem will not guarantee that this differential equation possesses a unique solution through the 0.53. Does it mean there is no solution? No, not necessarily, but it won't be necessarily unique. It doesn't guarantee a unique solution. Cool, cool? All right, well, that's all I have for you today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please hit like and subscribe. Thanks, bye.